All right. So solving by graphing is where we're going to start. And so I've just got several things going on here. With any system of equations, that first on your paper there, that first little block there at the top, there's a couple of blanks. With any system of equations, no matter what size, we're dealing with two variables, x and y. But if there are three variables or four variables or 16 variables, three things can happen. So there are three scenarios. And those are the three here. We're going to show the picture of what it looks like when there's one solution. Does anybody know what it looks like when two linear equations have one solution? What they intersect at one point. So you'll have one line. So draw yourself one line, and then just draw a different line that is not parallel to that, and they cross at one ordered pair. And we'll get that x and y depending on what the equations are out of that. So that one solution is where they cross, okay? So if you've got a three variable system, which we'll get into just a little bit, three variable system, what we're solving are the intersection of planes. And planes, you remember from geometry, are just flat surfaces. So a good picture of that is like thinking about this wall here in the front, this wall that goes down to the side, and then the ceiling. All three of those flat surfaces meet right up there in the corner where the ceiling touches both of those walls. That's a kind of a good visual of where there's one solution when you're dealing with three variables. If you're dealing with four variables, it gets a lot more complicated as far as drawing goes, and it's almost impossible to draw in 4 dimensions. We live in a 3D world. Drawing in 4 dimensions creates some motion in it, and it makes it very difficult to visualize what's happening. But it's one solution, means there's one answer for each variable in the system. That's all that means. The other option is that there's no solution. So if intersecting gets you one solution, what gets you no solutions? No intersections. What kind of lines never intersect? Parallel lines. So draw you a couple parallel lines on there. That's pretty close to parallel. Don't look like they're going to cross. Okay, parallel lines will never intersect. What do we know about the equations of parallel lines? The same what? Slope, the number in front of x. Yeah, so the same slope. Parallel lines have the same slope. And then infinitely many solutions or infinite solutions. What would that look like if intersecting is one solution, not intersecting or never touching is no solution? What would be infinite solutions? Yeah, they're laying right on top of each other, just smack dab on top of one another. So that's how we're going to draw that. So we're going to draw a line. And this one's hard to tell. So I just kind of try to make one of them shorter than the other to kind of try to show that there are two lines there that are lying right on top of each other. You cannot even count how many different ordered pairs that are solutions to that. And infinite solutions means everything works. No matter what x or what y we have in a two variable system. If it's a three variable system, an infinite solution might be an example of that would be maybe that wall and where the ceiling meets is a line. That line has an infinite set of coordinates to it. So that's an example of that. Or it could be where all three planes just lay on top of one another. That's also a solution or an infinite solution to three variables. But we're not going to have to draw three variables. I'm not going to make you do that. I had to do that before, but it's not a fun thing and it's not an easy thing to do. It's very difficult to do. But it's visualizing is not too difficult. All right, so let's look at a couple of these graphing problems and see if we can solve this system by graphing. That's the first method we're going to use. So what form are these two equations in number 1 in? Slope-intercept form. So we're going to graph each of those, and we're going to try to find where they cross. You've got to be really, really precise on your graphs. So that's why you need a straight edge, okay? So if you don't have something straight or a card or something like that, take you a couple of pieces of paper and just fold them and it'll make a straight edge wherever you fold it at, and that'll help you draw your lines really, really straight. It'll help you do this correctly. So let's graph that first one. I'm going to graph it with a blue line. Where do I start with that first equation? -6. So I'm going to go to -6, put a dot, and then the slope is -5/3. Well, if I go down 5, I get off the grid. So I'm going to go up 5 and left 3. We'll put that dot. I'm going to count that slope again. 1, 2, 3, 4, 5. 1, 2, 3. And then I'm going to draw that line. I'm going to try to be as accurate and precise as I can. And then I'm going to graph the second line on the same coordinate plane. Where does it start? It's its first point. 5 on the y-axis. 1, 2, 3, 4, 5. The slope is 1/6. I can go up 1 and over 6. I could go down 1 and left 6. And get them crossing there. And the good part about it is they cross at a nice point. That spot right there is the solution to this system of equations. So we need to write the ordered pair. So what is that ordered pair? 1, 2, 3, 4, 5, 6. So that's -6. 1, 2, 3, 4. -6, 4 is the solution to that ordered pair. Here's the beautiful part about this. If I take -6, 4 and plug it in for x and y in the equations, it works in both of those. So if I take -6 and plug it in to the first one, -5/3 times -6 would be a +10 -6, which is 4. So that gets the right y value. Same thing here. -6 times 1/6 would be -1 plus 5 is 4. So plugging it into both equations, it checks to be the correct solution to this. So we just found it by graphing. All right. Let's do number 2. So again, we're going to graph both of these on the same coordinate plane. How do you graph y = 5? Horizontal line where? Which axis? The y-axis. That's right. So we go up to 5 on the y-axis and draw our line. And then graph 2x plus 7. So graph it in red. So plus 7. And then 2x up 2 over 1. I could go down 2 over 1, left 1, and get the same line. That ordered pair right there is the solution. So what is that ordered pair? -1, 5. Really, really easy idea here about graphing and finding where they cross. Let's hop down there to number 3. What's wrong with those equations? They're not in slope-intercept form, so we need to get them there so that we can graph them easily. So the top one, I'm going to go over here and write 6x minus 5y equals -45. But just do a little bit of scratch work over here. I would subtract 6x. Give me -5y is equal to -6x minus 45. And then I would divide by -5. It's going to be 6 over 5x plus 9. And then I'm going to graph that. Should be that line right there. And I went down 6, left 5 to get that positive slope. I'm going to do the same kind of work here to the second equation. Subtract 2x. 2y is equal to negative 2x minus 4. Divide everybody by 2. Negative 1x minus 2. We'll go to negative 2. Put a dot. And then here's what I usually do. I usually will count that slope, the negative 1 slope, until it runs into the other line. And that will help me get the exact point out of this. So I'm going to count up 1, left 1 until I reach that point right there where it crosses that purple line. And I know that that is my solution. It'll be negative 5, 3. So if it's not in slope-intercept form, put it in slope-intercept form, and then you're going back to graphing. If you put them in slope-intercept form and the slopes are the same, but the y-intercepts are different, what do you know about those lines? They're parallel. Are they ever going to cross? No. If you get them in slope-intercept form and the equations are exactly the same, those are infinite solutions because it's going to be the exact same line graphed twice. Okay, so keep that in mind as you're doing the graphing there. The key is get them in slope-intercept form first before you do anything. If they've got a y and an x in them, make sure it's slope-intercept form, and then you just graph it. Really nothing else to that there. So flip over to the back there. We're going to go ahead and just talk about substitution, and I don't have these copy and pasted. I'm going to write it out. All right, so I'm going to look at number 7 first, which is y equals negative 7x minus 1, and y equals x minus 9. Up there at the top of your page, it has the instructions about how to do solving by substitution. Okay, it says solve one equation for either x or y, and then just isolate one of the variables. And then number 2 is substitute that resulting equation into the other one for that same variable, and then solve for what's left. And then we're going to get the other answer. So y'all have done substitution before, or should have. Both of these equations have to be in slope-intercept form, but I'm not going to graph them. I'm going to solve it by substitution. They're both equal to y. So it doesn't really matter which one I substitute into or with here because they're both solved for the same letter. So what I'm going to do is I'm going to take this second equation. I'm going to take the x minus 9, and I'm going to substitute x minus 9 in the place of y in that first equation. So it sets up the problem x minus 9 equals negative 7x minus 1. And then I'm going to try to get x by itself. I'm going to add 7x. I'm going to add 9. Divide by 8. I got x is equal to 1. Is that what y'all guys got? All right, so once I get that, I take that 1, and I'm going to plug it in to one of the equations to get y. I'm going to plug this in for x. It doesn't matter which one of those I plug into. I'm going to go to the second one because it looks a little easier than the first one does because it doesn't have that multiplying that's going on there. So I'm going to take that 1, put it in the place of that x. So that'd be y equals 1 minus 9, which is negative 8. So there's our x and our y. Our answer is the ordered pair 1, negative 8. This is the final answer. That ordered pair is what you're going to find for a solution here. Finding x and y by substitution, and then getting the ordered pair out of that. Look at number 8. Y equals negative 5x plus 30, and then 7x plus 3y equals 42. No. All right, so using substitution, we want to substitute or get one equation with one variable by itself. So the top one is already got y by itself. Have to be slope-intercept form, but it really doesn't matter which variable by itself, as long as one of them is. And then I can take that stuff and substitute that in the place of y in the other equation. Okay, so I'm not doing anything to the second equation because I don't need to. And then I'm just plugging in. Negative 5x plus 30. It's supposed to be equal to 42. And then I do the math there. Distribute 7x minus 15x plus 90 is equal to 42. So it'd be negative 8x plus 90 plus 42. What's the next step? Subtract 90. Negative 48, and then divide that by that negative 8. Positive 6. Okay, so all of that work, I finally disconnected from the computer. There we go. All right, so got x equals 6, and we're going to do what with that? We can plug that into the first equation. We could technically plug it into the second equation, but that seems like a little bit more work there. So I'm going to go to the first equation and plug in the 6 in the place of x. That ends up being negative 30 plus 30, which is 0. So our solution is the ordered pair 6, 0. Make sure it's x comma y. If they ever change the variable to like a's and b's or g's and h's or something like that, it's always in alphabetical order. Is the way the ordered pairs always go. Is alphabetical order. I think for the most part they use x and y's in everything we're doing today. Yeah, they use x's and y's. Okay, so there we had the first example of these had both equations where they were both equal to something by itself or a variable by itself. The second one where you had one equation that already had a variable by itself. Let's look at number 9. 6x minus 5y equals negative 28. And then the second equation is 7x plus y equals 22. So on this one, we don't have an equation that has a variable by itself, but I think it'd be pretty easy to get one. Which one would you think would be the best? Yeah, getting the second one with y by itself. If we can do that in one step, that's the way we want to go. So we've got the second one now with y by itself. Doesn't matter which variable you solve for, just pick one, and we pick the easiest one there. And then we're going to take that stuff and do what with it? Plug it in the place of x, in place of y in the first equation. So it's going to have only x's in it. 6x. Yes, ma'am.
I need it. You know what? I might not need it, person. Sorry.
Okay.
Apologize.
That's okay. Ain't on her hang up. All right. So plugging that in the place of y in the first equation, and then I'm going to solve that for x. So 6x plus 35x minus 110 equals negative 28. And then combine like terms there. The x's come together to get 41x minus 110 is negative 28. And then add the 110 to the negative 28. 41x. How much? 82. And then divide by 41. This works out real nice. X is 2. And then what do we do from there? Plug it back into one of the equations. It doesn't matter which one. Pick your favorite and plug it in. I've got one that says y equals, so I'm going to use it because it's less work. So y equals negative 7 parentheses 2 plus 22. That's negative 14 plus 22 is equal to y. So that would be 8. So the ordered pair, 2, 8. Good job. Again, ordered pair is your final answer, is what you're trying to go for there. Number 10 is a very similar problem. Let's go ahead and skip down to number 11 because it looks a little different. So I'm going to do number 11. 2y is equal to 6x plus 10. And then the second equation is 3x minus y is equal to 5. All right, we can get it to y equals, or we could get it to x equals. Technically, doesn't matter which one. I think it'd be pretty easy to get the top one to y equals because it's one step away, right? Yeah, all I got to do is divide everybody by 2. So that's going to give me y equals 3x plus 5. Yeah, then I'm taking that and plugging in that into the y place of the second one. So that's going to be 3x minus, and now here's where you got to be careful. You need to put that in parentheses, 3x plus 5. Yeah, because it changes the signs of everybody. If you don't distribute that negative, then it's going to mess the problem up. So here we end up with 3x minus 5 is equal to 5. When I combine the like terms there on that left side, they cancel each other out. And so there's no more x's. We get negative 5 is equal to 5. There you go. So this is a false statement that negative 5 never equals positive 5. So if the variables all cancel out, then you could have one of two scenarios. You could have a no solution, which is what this one is. If the statement is true, if it said negative 5 is equal to negative 5, that would be an all real numbers or an infinite solutions scenario. Okay, so the variables all have to cancel out when you're solving by substitution, or technically elimination does the same thing. But the variables all have to cancel out for it to be either a no solution or an infinitely many or an infinite solutions situation. And it's all dependent on whether that's true or not. If it's the same number on each side, then it's true. It's an infinite solution. If it's different, like this one is, then it's no solution. And you just write those words out. Write no solution. If it's infinite solutions, just write infinite solutions. Or you can just write the word infinite. As far as I'm not going to be too picky about that. Okay. Questions about this? Y'all remember doing this in Algebra 1? It's been a minute, but you remember doing it a little bit. You do this a little bit in geometry, but not a ton. It's a very, very small amount that comes up in geometry. But anyway, if you're